For the agenda, things I'll be covering today, I'll talk a little bit about my background. We'll just talk generally, what is a firewall, and obviously in the cloud. We'll talk generally about, cloud, just very simplified model, just to give some context. A little bit about the responsibility model within the cloud itself. So who's responsible, the cloud provider or the tenant? We'll cover a little bit about traditional networking versus cloud. We'll get into some well-known architectures for deployment strategies, how to put a firewall in the cloud, and then I have a couple of labs I think you'll find very interesting. And then the last exercise will be a simplified pricing model, just to give some context around pay-as-you-go versus bring your own license. All right, a little bit about my background. I've been in the industry a little over 30 years, started in 1991. At that time, we were working with stat muxes, green screens, and modems. I've seen a lot of transformations from traditional wired voice to voice over IP. I've seen the virtualization trend over the span of those 30 years, wired to wireless. So I've seen a few transformations, and now, so many things are going in the cloud and remote access, people working from home, especially with the pandemic. More about my background. Primarily my background's in routing and switching, so static routing, dynamic routing, switching, VLANs, just many different environments I've worked in, both from the SMB all the way up through the enterprise and carrier space. I've been focused on security for a little over 15 years, probably closer to 17, 18 years, being a trainer on several firewalls. So we're not only certified on the firewalls, most of them that are out there today in the market, but I've also implemented, again, small, medium space, all the way up to the carrier space, providing cloud-based firewall services, and then large enterprise, and then also been an instructor. So in virtualization and cloud, I've been working with that environment for probably about closer to 7 years. Just working in that environment, translating from traditional networking to virtualization, understanding cloud and how they differ. Certified in many different things, different products, firewalls, routing, switching, load balancers, helping customers with QoS, extensive experience with both legacy, traditional, and all the way through VXLAN networking. So why a firewall in the cloud? Well, first off, let's describe a firewall. So a firewall at its core is a stateful-based inspection model. So what does that mean? There's protocols, both UDP and TCP. UDP is stateless, TCP is stateful. In other words, there is a connection that's created when you set up a TCP connection, you get that full handshake. With UDP, we're just kind of tossing over the fence and we may or may not get a response. So with a stateful firewall, essentially what that means is when traffic comes to the firewall, there is a session built for the packet of interest. And based on that session, the return traffic coming back from the destination back to the original source is allowed by default. And therefore, the stateful base of the session isn't your traditional access list. So you only have to create a rule in the one direction. If you need the traffic to originate from the other source, then you need to create a policy from that direction as well. So from the standpoint of what constitutes a stateful firewall, we look at the slide here and we see that AWS security groups, they're stateful based. Azure network security groups, or NSGs, those are also stateful based. So those could be constituted as a stateful based firewall. Very rudimentary. They're not going to provide any advanced features. But we have other products on the market, FortiGate, Palo Alto, and many, many more, along with the firewalls that are in the cloud. Both AWS and Azure provide a firewall service, and that allows you to provide some enhanced features like IPS and a few features. They're somewhat limited in their capacity. So the differentiators, basically, next generation features. So what are we talking about there? We're talking about application visibility. We're talking IPS, IDS, malware detection, URL filtering, SSL deep packet inspection. These are all core to some of these, more advanced next generation firewalls, unlike what you're going to find within the AWS and Azure. Again, you can add some of those features to them, but you're not going to get all these in the core aspect of your firewalls for your next generation. So at the end of the day, the best firewall is the one that's configured correctly and utilizing these advanced features. So why a next generation firewall? Some of the things I just discussed, along with user and group integration. So as users come onto your network, whether they come onto your on-prem, whether they come on in some sort of DDI fashion, or whether they're logging directly into services, servers, databases, whatever it is within the cloud. So we can take that information and bring that into the firewall, and we can leverage that in our policies to ensure that the user or group is authorized to use that service. With application detection, we can actually identify, based on signatures, the actual application that's being leveraged. And with that information, that not only gives us visibility, but allows us to write rules and policies based on those applications and further tighten the controls around our firewall. So IPS and IDS, so intrusion prevention or detection. So those are, again, core features in next generation firewalls. They're getting updates, from the provider themselves on a regular basis. Those are all features, also features that are provided in the cloud as well. The malware and bot detection, again, these are signatures that can be on the next generation firewall, and provide you that additional capabilities to detect malware and botnet style traffic. The URL and DNS filtering. So URL filtering, that's really around client-based, keeping them off, bad sites, whether they're malicious or just inappropriate. So that's usually client-based. So if you're a SaaS or you're running VDI in the cloud, you can leverage this in your cloud firewall. DNS filtering, that's really about around protecting from an IP address standpoint, malicious sites, new domains, proxy sites. So these are all things you can take advantage of. And then the last bullet point, the SSL certificate inspection, validating that the certificate is actually valid. If it's not, you can actually block the site. And these are all built into the policies and you have choices. In addition to that, you have deep packet inspection. So the majority of the traffic that we're seeing today is SSL. That shouldn't be new news to anyone. But most of our firewalls are not necessarily doing deep packet inspection. So it is a little bit of a jump to get deep packet inspection working. And there's just some nuances around, how to deal with one-offs and certificates that may not be valid. So these are just, again, features that you can leverage, whether it's an on-prem firewall or a firewall that's in the cloud that has this as a core feature. And again, just, reiterate, you could have a next generation firewall within your environment. If it's not configured correctly, it's really no better than not having a firewall. It might be a little bit better, right? I mean, if you just have any rules in there. So a properly configured firewall, leveraging the advanced features appropriately, is really where you want to be. So cloud simplified. So cloud is made up of a host of services. There's all kinds of services, both in AWS and Azure. Many of you may have taken advantage of some of these features in different capacities. At the core, it's made up of compute, memory, storage, and networking. So if you've built your environment in the cloud, or you're thinking about building your environment in your cloud, you've built it around kind of traditional networking, right? You've got a private address space, which is either your virtual private cloud, VPC, or VNet, virtual network, right? AWS or Azure. And then within those, you're building up subnets, routers, all your networking, and then you're building your servers and attaching them in that environment. So how is the cloud different? It looks and feels like a traditional network. So first of all, let's talk about the separation of responsibilities. So on the far left, if you're on premise, right, you need to manage all the different layers from networking, storage, servers, virtualization, all the way up through your applications. If we go to the infrastructure as a service, now we can see that someone else manages the networking, storage, service, virtualization. That's, again, the cloud provider's responsibility. And then we're responsible for putting that OS on there, any middleware, runtime, data, application. So it is our responsibility to secure that data and make sure that OS and any middleware is configured correctly for the environment, and that's meeting the requirements not only from a business standpoint, but from a security standpoint. When you get up to platform as a service, right now you're just looking at data, the applications. While containers is not in this, you could add another section around containers, and then software as a service at the end. Basically, the cloud provider manages the entire stack. So this shouldn't be a new slide to anybody, but if you haven't seen this before, that's kind of a breakdown. So let's do a brief layer 1 through 3 discussion, kind of the difference in the cloud versus traditional networking. So at layer 2, in the upper right-hand corner, we see traditional MAC learning. So in traditional networking, whether it's a large enterprise or a small mom and pop, location, they have a switch, a couple computers, or maybe you have multiple switches, you got a core, you got an aggregation layer, you got multi-campus, whatever the environment might be, whether it's in wired and wireless. The way MAC addresses are learned within that environment are through broadcasts. So these broadcasts are sent out through the environment. The switch will then collect that information, forward that through a broadcast if it doesn't know of the destination device that they're trying to get to, and it will continue to build this MAC address table. So the MAC address table within each switch is what's leveraged to minimize those broadcasts. So next time someone wants to talk to a device through the switch, it might be through a switch and a router and many other things, it's going to leverage its MAC address table that's built to minimize those broadcasts and forward that traffic on the specified port that it learned the MAC address on. So that's all good. Somebody swaps out their PC, they get a brand new PC, they connect it to the switch. It's now a new MAC address. The switch needs to learn that MAC address and allow traffic to forward. So the switch has that all built in. It's got a MAC address learning table. If we look at cloud, so we're looking at the bottom section now, either AWS or Azure, essentially they operate the same. There might be some nuances or little differences, and the database at the bottom is just simply an example of what that might look like. But what happens when your instance is built, right? Your instance is built, it's associated with the NIC. That NIC is built as well, and during the time of configuration, you can either specify a static IP within the subnet that you create, or you can allow it to automatically create one. So when this NIC is built and that address is created statically by you or dynamically, it's built in a database. So once that database is built, we no longer have this broadcast issue of identifying where the MAC address is and or how to determine the MAC address someone's trying to go to, whether it's layer 2 or layer 3. So that minimizes that MAC broadcast of traditional networking. On the left side, AWS, if you're doing troubleshooting, AWS is going to provide the real MAC address of the device it's going to. And Azure is actually going to provide a fake MAC address. So if you haven't seen this before and you're ever in Azure, just do an ARP-A, or look at your ARP table, you will see that MAC address. Also to keep in mind on the cloud, so there is the route service, and that's just it, it's a route service. So it's going to do lookups to the databases to determine where the traffic needs to go. So if we look at layer 3, on the top, we have a similar diagram. Now we're going through a router. Now the router might have multiple VRFs, might be a single router, but what's important here is that the router is going to rely on connected networks, so directly connected to a switch, static routes, how do I get there? Maybe I got a next step router, or dynamic routing, which means I'm learning some sort of route, right? But this router in the top left is actually a point or a hop between these two machines. So that's a key thing to remember. On the bottom, if we're looking at the cloud routing, right, we're looking back at that database again. So it is a route service. It's not a hop between these two machines. So we're looking up in the database and we're looking up against three different priorities, right? There's always going to be a system router or route service, if you will, and that's going to have what's built around the, whether it's a VPC or VNet. And then you can leverage BGP on top of that, dynamic routing, to learn those routes within your environment. That might be a route that's learned from a direct connect back to your on-prem, a VPN to another cloud service, whatever that might be. You can leverage BGP. And then where you have UDR or static routes. UDR is user-defined routes. So UDR or static routes are always going to be first priority. And this is for an equally masked or an equally route between these. So UDR is going to be first priority, BGP is going to be second priority, and the system is going to be the third priority. So again, biggest catch here is, a traditional network, this router is actually is a hop between. In the cloud networking, this is a route service. It's just looking at a database to determine where the packet needs to go. So if we look at a couple of deployment architectures, I'm not going to spend a bunch of time on these. These are well documented, and you get some of these architectures on GitHub. But if we look at the left side, there's a single firewall. You basically have an external and internal subnet. From there, you have some sort of protected network that's behind that, and a UDR. And if you, like I said, if you go to GitHub, you can launch these. It's pretty easy to do. Get that set up. You can get a machine in there, even for some basic testing. On the right side, you've got a HA pair of firewalls. And the HA pair of firewalls, you can see that there's 4 different interfaces there to traditional HA, in this case, FortiGate firewalls, using their FGCP or FortiGate clustering protocol. So it requires an HA sync, requires a management interface. You still have your internal and external. You can wrap that with load balancers. So there's lots of things you can do there. On the back side, on the far right, we've got a couple of protected networks. These are things, areas where you can put, front-end web servers, back-end databases, and so forth. So to expand on the FortiGate firewalls in Azure, in this case, we got a couple of firewalls. We can see that they're in 2 different availability zones. So now this increases your availability. So if an availability zone does go down, you have the other firewall acting as also acting as an available firewall. In this case, they're active, and we do have them wrapped with a load balancer. So the load balancer is going to send traffic through each firewall from a load balancing perspective and handle the traffic from that regard. So from a deployment strategy or architecture in Azure, here we can see we got a couple of firewalls on the left side. They're acting as a security context. Off to the right side, we have multiple VNets, and we have UDRs set up pointing that traffic towards the firewall. So I'll actually be doing this in my lab, so we'll see this here in a moment. If we're looking at AWS, very similar modeling. We have a couple of FortiGates here acting as active-active. They could be active-passive, but there's lots of different ways to deploy this. In this particular model, we can see we're in AZ1, availability zone 1 in AWS. And we've got an internet gateway, we got an intrinsic router, and we've got the HA set up, both HA sync and HA management on the right side there for the firewalls to either do FGCP, which is a FortiGate clustering protocol. And again, HA, every firewall is a little bit different. They have their different protocols, if you will, for their HA. FortiGate has many different ways of doing HA. The clustering protocol is one. There's also a session firewall sync as well. And that works really well in the cloud environment. So another architecture, ran into this a little over a year ago. This is the gateway load balancer and service endpoint within AWS. As you can see, the numbers that diagram there. We have a security VPC off to the right. We have our FortiGate firewall deployed, and it's listening to what's called a Geneve protocol. It's actually running on TCP 6081. and then traffic is being forwarded from the gateway load balancer. And the gateway load balancer is right there in the security VPC. And so as we see traffic coming to or going from the instance, we can see whether it's coming in through our internet gateway, it's being sent to the gateway load balancer endpoint, being redirected to our FortiGate firewall, processed through policies, and then returned back to the endpoint and onto the instance. And then you get the reverse. If the traffic is leaving the instance and app subnet 2, you've got traffic going to your gateway load balance endpoint. It's being sent over to the load balancer and ultimately to the FortiGate, again being processed by policies, sent back to the endpoint and out to the internet. So I thought this was kind of interesting. There's no need for a transit gateway to send traffic to your security VPC. Speaking of transit gateway, so in this case, this will also be part of my lab. I've got a couple of VPCs similar. Off to the right, we got a security VPC. Now on this lab, they're actually showing it going to a gateway load balancer. In my lab, I'm actually just going to push it straight to the firewall, so I'm not going to use the unique interface for the traffic. The previous diagram where I have the single VPC and internet will be using the unique interface. But as we can see here, the two left VPCs, they both have internet gateway, and they can both go out the internet just fine. However, when they want to talk to each other, they're forced to go through the transit gateway, go through the FortiGate firewall to get processed through policies and inspection before they talk directly to each other. So again, it's providing the visibility, it's providing the security, and it's providing any advanced features, which could be SSL, deep packet inspection, IPS, all the things we talked about previously. All right, so I'll get on to my lab. So I got a couple of labs I want to just kind of walk through. I'll go through my diagrams briefly, then I'll actually get on Azure. Azure will be the first one here. I'll talk through some of the components, and I'll give you, just show you some basic pings and show you that things are functioning as expected. And then we'll move on to AWS in a similar fashion. So on the Azure Lab that I have here, it's similar to the diagrams we saw previously. On the left side, we have the security VPC, the security VNet. We are in Azure. I have 3 subnets defined. I've got a public one, a private one, and my firewall is deployed and attached to these 2. And then I have a protected network, which I have a Windows machine launched in. And that protected subnet also has a route table associated, and we'll see the UDR routes there that we've defined. On the left side, we have a couple of VNets, VNet 01 and VNet 02. They each have just a single subnet in them, and they each have their own route table as well. All right, so within my Azure network, I talked about having a couple of different VNets, and so I've got the VNet here. Just making sure my screen was sharing. So I've got the 3 VNets. I got my security VNet, I've got my VNet 01, and I've got my VNet 02. So 3 separate VNets. Within my VNet, I'm doing peering from my security to my 2 VNets. So they're connected with each other. If I go to my route tables, and I look at my security protected route table. So this is one of my protected subnet. I can see that I have a few routes defined here. And if I come down and look at my effective routes, we come down and we see that we have some user defined routes for specific networks, including a default route, and they're all pointing to this 10.0.11.4. Now 10.0.11.4 is actually my private IP address on my FortiGate, and we'll see that here shortly. From there, I've got 4 virtual machines. The top one here is my FortiGate. That's going to be providing my security and policies. I have my Windows machine on my protected network, my 2 Windows machine on the other 2 VNets. All right, so if I log into my FortiGate, So we already see we have a lot of traffic there. I wanted to make sure and generate some traffic before we had the webinar here. We can see the address here, 10.0.11.4. So that's been defined here, and that's where my UDR traffic is being pointed to on all of my protected networks across all 3 VNets. We have some static routes here. So all my internal networking is pointing back to my 10.0.11.1, which would be that route service or intrinsic router within Azure. And then if I come down to my policy and objects, I see from a firewall policy standpoint, all my traffic, or most of my traffic, is going to be coming in from port 2 and going to port 2, right? So any traffic going between any of the protected subnets within Azure is going to go through, going to be forwarded to port 2, which is my 10.0.11.4, processed through the policies, and then back out port 2 and on its way to its destination. So I have several policies here to accommodate that. If I come up a little further, I've got my port 1, which is my public or internet port, which is allowing me to do RDP into the environment. And I'll be pulling up my RDP session here in just a moment. And then I've got port 2, which is again my private. So those protected subnets sending traffic out to the internet will be traveling, passing traffic from port 2 to port 1. And in most cases, I have application inspection turned on. And in this one instance, I have deep packet inspection. So I'll show you that as well. All right, so if I come over here to my Azure environment, let me bring this screen over. So this is my protected network on Azure. This is sitting in the same VNet as my FortiGate. It's on 10.0.100 network. And as we can see here, I can ping out to the internet just fine. And just to validate that, I'm going to come back to my firewall briefly. Checking my time. Time is good. We'll do is fine. Host 10.0.100.4 and ICMP. Otherwise, we'll see a bunch of other traffic. So we have our ICMP set up here. I ping out the internet. Come over here and I can see this on my firewall. I'm pinging to 888. It's coming from 10.0.100.4. So we can see the traffic's actually hitting the firewall as intended. Now I can also ping the other locations. So 10.100.10.4 is my VNet 01. So we're pinging that there. And I can ping 10.101.10.4. And if we come back to our FortiGate firewall, we can see that that traffic is passing through the FortiGate as intended. Now we talked a little bit about inspection. So if I run browser here, obviously I can get to Google fine. If I go to icar.org, it's just a test website. It's been out there for quite a while, but it's a way to test malware. So if we look at our certificate here, we can see that it says the communication is valid. If I look at the certificate, I can see that it's issued by R3, issued to eicar.org. That all looks good. So from downloading a virus, again, a test virus, I can see that this gets through just fine, right? The firewall's not going to see this traffic unless, however, I am doing deep packet inspection. So let's look at that. I'm going to go over to 10.101.10.4. And 10.1.10.104, I'll actually come back here for just a moment and just revisit the firewall policy. We can see here that 10.1.10, 10.4 in this policy has deep packet inspection enabled on it. So I'm going to come back here. I come back to the 10.101.10.4. And I'm going to go ahead and go to the same website, eicar.org. All right, we get there, we see we got a good padlock. As I come down and look at the connection is secure, if I check the certificate, I can now see that I am signing the certificate on behalf of eicar.org from my firewall. So there is just a few steps to on the firewall to actually make this work. There's a few more steps from a certificate perspective that takes a bit more time. But I'll go ahead and launch the file again. So here, my firewall is now actually seeing this, and it's actually blocking it as intended. So if I come back to my firewall, and I come down here to log and reports, forward traffic, and I can see I got a block here. It's a UTM block. And as I come down here further, we've got a different block. Oops, actually I wanted to see that. Security. We can see that the file name was icar.com. So we can see that the firewall actually decrypted the traffic, even though it was SSL. It was able to detect that this was a virus, even though it doesn't have teeth in it, and it was able to block it as expected. All right, I'm going to come back here to my presentation. We'll go on to the Azure Lab. So the Azure Lab is a little more complicated, quite a bit more complicated. We're using a transit gateway in the center. As I mentioned in this upper VPC up here, I do have a public address coming in. I've got an internet gateway connection. They are isolated to their own route table. And then I've got a gateway load balancer endpoint, as described earlier in my discussion. This traffic from the internet, from this instance to or from the internet, is going to go to this gateway load balancer endpoint, which traverses over to the endpoint service, into the gateway load balancer, over Geneve protocol, and to the firewall. So we'll see some of that on the firewall. I'll show you some of the components there. But as you can see, all these routers I have here, I've spoken of my transit gateway. Each subnet has their own route table all the way through. So think of it from a perspective of, if I have traffic that's leaving an instance or landing in a subnet, when it hits that subnet and it needs to go somewhere else, it needs to look at a route table to get there, or it's going to take just the main default route table. And the main default route table is going to allow it to go anywhere. So essentially, we're overriding a lot of the main routing tables by inserting a unique route table in each one of these subnets to ensure that the traffic flows the way we want it to. Let's see anything else here. You'll notice I have a transit gateway subnet here. That's again, so this traffic can land on the transit gateway, and then a routing decision can be made to send it to the firewall. Let's go ahead and get to the lab here. All right, like I said, a little more complicated. I've got about 10, 15 minutes, so I'm going to kind of go through there somewhat quickly. So I have the 3 VPCs I talked about, the security VPC, VPC 01 and 02. I've got multiple subnets, each one having their own subnet, and the security VPC having multiple subnets. As I mentioned before, I've got multiple route tables, so you can see these 3 are the only main route tables. These get actually created when you create your VPC. The other route tables are route tables that I have engineered the routing to send the traffic in the direction I want it to go. So without getting into all the details of the route table, I mentioned I have a couple internet gateways, one on my security VPC and one on my VPC 01. That's for that internet traffic. And if I look down a little further, I've got a couple elastic IPs that will be primarily going to this one, showing the demo. And further down, I've got my endpoint. Again, the endpoint is what's going to encapsulate that traffic and send it over to the FortiGate. And then you've got your endpoint service. This endpoint service is actually associated with my gateway load balancer. So if we look at the load balancer here, we can see that I have a gateway load balancer established. If we come down further here, I do have a transit gateway, just a single transit gateway. I've got the attachments to the 3 VPCs as described in the diagram. And then I've got multiple transit gateway route tables. And again, having multiple transit gateway route tables allows you to restrict traffic. So in the spokes, when they get to the this route table, the only route they know is to go to that transit gateway subnet within the security VPC. Otherwise, a traditional route table would just allow the spokes to talk directly to each other. If I come over here to my EC2, I have my multiple virtual machines. Again, I have my FortiGate. We'll be getting on that here in just a moment. I've got my Windows security and my protected subnet, my Windows and VPC-01, and then Windows and VPC-02. So those are all listed here. Let's see if there's any more. The load balancer. So we've got a load balancer here. We talked about that just a moment ago. I got the gateway load balancer, and then it has a target group. So I come back over here, come over to my firewall on AWS. All right, again, we're seeing quite a bit of traffic here. So let's come down here to interfaces. We mentioned before that the gateway load balancer is sending traffic 10.0.11.204. If I expand port 2, we can actually see this AWS Geneve, just a generic name, but this is basically like a VPN tunnel that the gateway load balancer is going to send traffic to. From here, we got our static routes. Again, fully supported with dynamic routing. Most of our routes here are going to 10.0.11.1 or internal. This zero network route is here for just simply making sure traffic can pass back out the interface. Without this route, it wouldn't be able to pass back out. And so it's just got a higher priority. It's really not doing anything other than just validating the route can pass back out the same interface. I do have a policy route stating that anything comes in for this particular interface or any source, any destination, it's going to be forced back out the same interface. And so those static routes and the policy routes kind of work together there. If I get down to my policies, so I've got similar policies. So my first 3 policies are from my AWS Geneve protocol. I've got my IP coming in, allowing me to go to RDP. I've got, in this case, allowing it to go to the VPC-01, leveraging RDP. I've got HTTP traffic, and if we scroll off here, we're allowing both HTTP and HTTPS. Again, this is through the tunnel Geneve protocol. And I have deep packet inspection here as well, so I'll display that, or show that when I get into the machines there. And then we have a very similar, so we got port 2 to port 1. This is for internet outbound for these 2 protected networks. And then we have a lot of port 2 to port 2. Again, traffic's coming to the firewall through route engineering, if you want to call it that, through the transit gateway and all the different routing tables to force traffic down the path we want it to take. And it's for VPC to VPC. It's going to come in port 2, process through the firewall rules, and then go back out port 2. All right, so if we come over here to our display it over here. All right, so we're coming in our public address, coming into the protected network, which is 10.0.100, 217 for this particular IP. We can look and see if I can ping 888 okay. And I want to come back over to the firewall and smoker packet. We do a host 10.0.100.217 and ICMP. Otherwise, I'd be seeing all the RDP traffic as well, so I'm going to filter it down. See what happened to 10.0. Oh, sorry, got ahead of myself. Okay, let's get back over here so I can ping the internet as expected. And I can see on the firewall that I'm actually seeing that traffic. Well, I can ping the 10.101, 10.177. And I can ping the 10.100.10.201. And these are just the IP addresses that are what's randomly associated. And if I come up here and I can see that traffic, so 10.0, 10.17 to 10.101.10, and then to 10.100, 10.201. So the two IP addresses I pinged, we can see that the firewall is seeing the traffic. So I'll come back over here to my firewall and I launch Internet Explorer. And I'm gonna go to EICAR again. So I'm on 10.0.100.217. And if you recall where I put my deep packet inspection, this guy here, I put it against this particular IP address, 10.100.10.0. So we expect this to fail or the firewall not be able to see it. So we got our full EICAR here. Doesn't not allow me to click on it. That's okay. If I go to download my virus file, and I click on any one of these, but we can see that that was unsafe. The actual text in the body came through, so we would technically be infected from this machine. So if I come over to 10.100.10.201, all right, so this is the one I actually have my deep packet inspection on. From here, I can ping Google just fine. And if I come over here and open up Chrome, okay, we landed on the same page here. We look at the certificate again, connection secure. Let's look at the certificate. Again, it's being signed by the FortiGate firewall itself. So we go over here and download our text file, or our test file, and I can click on any one of these. And we can see we got a high security alert and that the file was blocked. So if we come back to our FortiGate firewall, we should have hit this rule up here. So I'm going to come down to logs. And this first rule here, I can see I'm on the AWS Geneva. Basically, it's a VPN. If I go over to my security here, I can see that I downloaded an icar.com text file, and it was infected and blocked as expected. All right, so that's my two labs. Just a quick pricing exercise, and then we'll get to some of the questions if we have any. On the left side, so this is a very simplified pricing, right? On the left side, this is a pay-as-you-go model versus bring your own license. So, you know, at the end of the day, when you launch the FortiGate, whether you bring your license or pay-as-you-go, you're going to pay some charge, right? So as pay-as-you-go, you're going to pay the 17 cents per infrastructure cost, and then you're going to pay 85 cents an hour for the licensing, right? If you come over, you bring your own license, we'll see the same model. We're still paying for that infrastructure cost, but we no longer have a licensing because we're bringing our own license. So general cost, right? If we look at the C5 large, that would be the next one down here. It's basically 81.5, right, just over 81 cents per hour as a total. That total, if we ran it for a full year, right, $7,139. If we run the same thing over here for a full year, we're talking about, you know, 2,419, and that includes the actual license itself. So you can, you know, reduce those costs by committing to an annual price within. This happens to be AWS. Apologize if I didn't describe that earlier. But again, just understand your pricing model, and you know, whether you're doing HA, auto scaling, whether it's temporary, you know, keep the pricing in mind. If it's, you know, the cutoff seems to be around 4 to 5 months. If it's going to be longer than 4 or 5 months, you probably want to bring your own license. If it's very temporary, or if you're doing auto scale, you can do a bring your own license, right, for your base FortiGate, and then do pay as you go for firewalls that may expand as the need or bandwidth increases. So again, just a simplified model, just to give kind of some context around that. All right, thank you very much, everybody. Feel free to reach out if you have any additional questions or need some assistance, or, you know, from an architecture or deployment perspective. Thank you.